Hi, everyone. My name is Brian Janger. I'm here with the CS 101 Reviewer App team, along with my teammates Belle Xu, Manith Luthria, and Sona Suryadevara. And here we're just going to talk about our accomplishments over the summer with the CS 101 Reviewer App. And we have project lead, Professor Stephens Martinez, and our mentor, Adam here. So quick overview. What is the CS 101 Reviewer App? It's an online web application that students use throughout the semester in CS 101 as an optional study tool and also for pre-lab activities. And there are a bunch of machine-generated questions involving various topics throughout the course. So we already had a baseline version of the app to work with, but we had 4 main projects that we worked on over the summer, divided into 2 main focus areas. The first was app development, where we worked on generating more types of questions and implementing a new teacher dashboard feature. And we also had 2 data analysis projects. One of them was about frequent misconceptions that we could find in the app, and the other was about office hours analysis in CS 101. So reiterating a bit here, the CS 101 Reviewer app is a web app that's got machine-generated multiple choice code tracing questions. And that's all the app is, essentially, just divided into several different topics like lists, recursion, etc. So you can customize your quiz as a student to do certain topics, or you can also generate topics randomly, depending on your mastery in certain topics. And this is a bit of an example of our question generator. So each one is organized by concept and a topic involved. Basically a sub-concept for each concept. So in this example, we have a list with for loops involved, right? And there's a template for every question where different variables in said question or different statements will be randomized. And in this case, the list numbers are randomized, as well as the number in that if statement, which can change the different types of answers and different types of iterating that students might need to do. And so we can see there are 4 automatically generated answers. One of them is the correct answer, and then the other 3 are generated based on what mistakes we would expect a student to make when we're doing this type of question. So we each worked on a different topic. I worked on Boolean statements, Belle worked on simple if statements, Manith did multiples, and Sona worked on for and while loops.
The second feature that we added to the CS1 Reviewer app was the teacher dashboard, which essentially the purpose of it was to provide teachers with data about how the students are performing in the class. Specifically, what our teacher dashboard does at the moment is it provides data to the teachers about whether or not students completed the pre-lab, which is done through the CS101 Reviewer app. To do this, we used Flask, PostgreSQL, HTML, CSS, and JavaScript. And we chose these tools because that's how the website was already formatted. So a big part of this project was for Brian and I to learn how to use these tools. The steps we used to create the teacher dashboard was firstly to research possible features, which meant asking instructors and professors of CS 101 what they wanted to see out of a teacher dashboard and what would be useful for them. Then we had to learn to use tools, as I previously stated. Next, we created a CSV download using the SQL database and picking the data we wanted from that SQL database in the back end. Next, we created the web page and the entire front end, and then we deployed the feature to the website. Next slide. This is a student view of the CS 101 Reviewer app. Essentially, for a pre-lab, what the students will do is they'll generate a random number of questions, or no, sorry, they'll randomly generate a number of questions, and that will be their pre-lab before they go to lab. Next slide. This is what the teacher will see when trying to download data about their students. They'll pick a start date and an end date, a time frame with which they want to see data, and then they will be able to see in that CSV whether or not students completed the pre-lab as they were supposed to. Next slide.
During the summer, we conducted 2 data analysis projects, and I'm going to talk about the first one on frequent misconceptions. So for instructors, understanding misconceptions and their related causes is just as important as understanding the course material itself. Although there has been a lot of work on listing misconceptions in courses like CS 101, there was a lack of work on automatically identifying them and also updating instructors on student behavior. So we asked ourselves, what information can we gain from our reviewer app? So in our data analysis, we'll answer 3 main questions. First of all, we'll verify whether students are randomly guessing when they gave an incorrect response. Second of all, we're going to try to identify the frequently occurring labels and examine them in context of all question responses. And thirdly, we'll try to see if there is any differences in student behavior across the semesters. So our data are mainly response data that directly came from the reviewer app for CS 101 in fall 2020 and spring 2021. The reviewer app was presented as an optional study tool for exams, as well as required pre-lab activities in 3 of the labs in fall 2020 and 4 of the labs in spring 2021. All our data analysis is basically organized by pre-labs as well as their pre-assigned concepts and topics, as you can see on the table on the right. And all the analysis are done through R and tidyverse packages. So for our first research question, we aim to answer whether students are randomly guessing. So to do this, we first assume that students would be guessing among the wrong options uniformly at random if they gave us an incorrect response. We did this by calculating the expected counts and the actual counts of each label. And then we directly compared those 2 distributions using Pearson's chi-square test. And as you can see in the results on the right, there's only 2 labs that yielded close to, or one of them is actually statistically significant result. So we can say that students are not randomly guessing in Lab B Spring 21, and the Lab A one was close to being significant. However, we used Bonferroni correction significance level in all of our hypothesis tests, which is basically correcting the 0.05 significance level and divided by the number of hypothesis tests we're conducting. So under this correction, Lab A's results were actually not significant. Next slide, please. However, we still examined those 2 labs mainly by conducting a bootstrapping process and developing a 99% confidence interval for the expected chosen counts for each label. And you can see on the top graph on the right, this is an example graph for our confidence interval and actual chosen count comparison for Lab B. And so out of the 2 labs we mentioned earlier, we found 3 significant labels, which is append is concat, which is like mistaking list appending to another list as list concatenation, and return does not end, return statement doesn't end the function, and list comp is first value, which is list comprehension only processes the first value instead of going through like the entire list. So we further examined those 3 significant labels, and we wanted to see whether there's any differences in context of student performance. So first of all, we compared each student's performance on questions with options associated with each of those labels versus questions without those labels. So we can see in table 1 that there's only 2 labels that had a significant difference, which is append is concat and return does not end. And then we again focused on those significant results and tried to see whether there is a significant correlation between student performance on questions not associated with those labels versus the proneness of each student to this label. The proneness is measured by the amount of times a student sees this label and the amount of times a student actually chooses this label. And we can see that there's only a very weak correlation between those 2 statistics for append is concat through this Pearson correlation test. And finally, we compared the differences across the 2 semesters. So first of all, again, we're going to examine this from a student performance perspective. And through a Mann-Whitney U-test, we found that there's no significant difference between students' score distributions across the 2 semesters in the 2 labs that we examined. Also, it is worth noting that we only examined Lab A and C instead of all 4 labs because only Lab A and C had matching concepts and topics. And however, even though the student score distributions are statistically similar, students were actually biased towards the same ranking of misconception labels only in lab A, but not in lab C. As we can see in table 2, there's only the lab A's p-value is actually significant.
Okay, I'm going to talk about the second part of our data analysis, which is scaffolding help in office hours. So this is important to understand because there are inconsistencies between teacher office hours help and what the student think they're getting as help. So it's important to analyze the data. We need more plans to improve office hours interactions using existing office hours data as well. We have many research questions, but a couple selected research questions that I'll talk about are how do our wait times, interaction times, and TA time distributions compare to related work given our scaffolding of help requests? And how similar are student responses compared to teachers? And we'll be looking at 2 questions that they both responded to. Next slide, please. Okay, so both teachers and students use the website of My Digital Hand for office hours interactions. We analyzed the data from 4 different courses. 2 are CS 101, but one is in the fall 2020 semester, one is spring 2021, and then also CS 201 and CS 216 courses. So while the teachers and students have interactions on office hours or on My Digital Hand, they both fill out feedback forms before and after their interactions based on different questions that the professors decide to ask them. This analysis was organized by form question and interaction and wait time data, and it was done through Python, Pandas, and Seaborn programs. So first, we analyze interaction times, wait times, and the Hamming distance. So first, mean interaction times that we could see in the table on the slide before, they were all between 14 to 19 minutes. And mean wait times for all courses were between 5 to 9 minutes. Overall, this is very good perception of all of our courses, office hours interactions, and overall, it's a good wait time and interaction time. It's what we expect. And out of all 1840 total wait times in the data, only 6 were above 1 hour, which is also really good to see. Next is the Hamming distance. So the Hamming distance is the number of positions at which the corresponding symbols are different. So we looked at a question, and based on it was a multiple choice question with you can select as many options as you want. So based on what the student selected and what the teacher selected, we kind of calculated the Hamming distance between where there were inconsistencies between their answer choices. So as you can see in graph 2, we have the Hamming distances for all 4 courses graphed on here. And all of them are around the 1 to 1.5 range, which means there were around 1 to 2 options that were inconsistent between student and teacher interactions in office hours. Yes, next, please. Another question we analyzed was how did the interaction go? And for this, we used heat maps. So these heat maps show the inconsistencies between the student and teacher answers for this question. So this question was a multiple choice question, and it wasn't select all or select many. So we were able to do heat maps for this. So the answer choices, as you can see on the left, where the student was able to finish, student should be able to finish on their own, and the student will need more help, and the student did not make any progress. So these are 2 different example graphs that we selected from the 4 different courses. And as you can see, they are very different results. The graph on the left shows many inconsistent results. So the diagonal with 30, 17, 6, and 0 are where where student and teacher answers are consistent. Any other square but that diagonal are where they are inconsistent. So as you can see, there are many inconsistencies. For example, for the square labeled 16, the teacher put the student should be able to finish on their own, and the student put the student will need more help. And so this is very important to know what the teacher and student were both thinking of their interaction and how they felt after the interaction. On the right-hand side, we can see this graph is pretty consistent. There aren't many inconsistencies between the student and teacher answers, which is good to have, which is good to know the different results that vary between each course. Next slide, please. So lastly, we analyzed the question that asked the student, what do you need, the student and the teacher, what did they need help with? So I asked the student before the office hours interaction, what do you need help with? And I asked the teacher after the hours interactions, what did the student need help with? So as you can see, this is an intersection graph of one of the courses, and there are inconsistencies in the student and teacher answers in regards to the 7-step process. So for the columns, there's one is for step 1, one is for steps 3 and 4 of the 7 steps, one is step 5 and one is step 6. And as you can see, the most inconsistencies are between step 5 and step 6. And it seems that the student was more likely to put that they were writing the code to solve a problem or testing their program, while the teacher was most likely to put that the student was developing a plan to solve a problem. So this is a major finding, that there was an inconsistency between student and teacher answers for this course, and this can inform decisions about future office hours interactions. Yes, thank you. That's my section.
All right, so we did 4 different projects this summer, and we learned a lot. Most importantly, what we learned is how to work in a team, specifically how to work in a virtual team environment. We also learned skills like improving our programming and our data analysis skills using features like Git, Python, specifically pandas, R, Flask, SQL, and stuff like that. We also learned the research process and how to think critically, and for Belle and Sona, how to write papers. And then lastly, we learned hard skills like web development and data analysis, things like that. Next slide. We'd like to thank our graduate mentor, Adam Carricker, and our project lead, Professor Stevens Martinez. And also we'd like to thank Professors Fain and Tackett for helping us with our data analysis. Thanks, guys.